Hey, so we had a question on Piazza, and I think it's a good one. I think a lot of people probably would have this similar question, so let's go through and try to answer this. And it's the general question of brightness in bulbs, which is something we're going to be talking about a lot the next couple of weeks. And so first of all, brightness is the same thing as power. So the power that a light bulb is giving off is going to be equivalent to its brightness. And the standard definition for power is the current going through your, for instance, now we're talking about the power going through a resistor. And so it's the current going through the resistor times the voltage drop of the resistor. And in a similar way to the equation we had for the energy stored in a capacitor, right, we can take Ohm's law, which is, V or delta V is equal to I times R. So sometimes they write this as delta V or V. It's all sort of the same thing as the voltage drop. But with that equation, you can take this one and write it in different ways. And so there'll be a lot of cases where there'll be like two, and usually they're identical. So like maybe two resistors in your circuit that have the same resistance. And we'll ask which one is brighter, for instance. And so the thing is if you look at this equation here, these ones are usually a little bit easier to work with. So if we assume that they're the same resistance, then basically the one with the bigger current going through it or the one with the bigger voltage drop will be the one that's brighter. All right? And so generally, usually there's one way, one of those will be a little bit quicker than the other one. You get sort of better at it. Either one should work. But basically, if there's a quick way, you can kind of realize that. That's how, one of the best ways to sort of think about that. Now, it is a lot to get your head around right now, and so let's just go through and look at the two simplest examples and try to explain them, because the person who posted on Piazza was really curious about these two examples. And so here's the first example, which is when you have a light bulb, which again, a light bulb is the same thing as a resistor that's set up in series. So again, series means that if I go through the top one and keep going, I have to go through the bottom one. All right, and so what happens in this particular case here, so we asked, a light bulb is connected to a battery in case A. In case B, an identical light bulb is added in series. What happens to the brightness of the original bulb? And so this is, I think, something that the person was confused about, so let's talk about it. So it decreases. And so there's lots of ways to think about this, but I think the way we tend to try to think about this at first is to always think about this sort of in terms of the world's simplest circuit, which is like one battery and one element. So right now here we have one battery, one element. So let's say this is V and that this is R. Right? When I have the simplest circuit in the world of a resistor, then to find the current, and so I'll call it the current for A, it's just V divided by R would be the current. So the current comes out of here, it would be so again, if you were to increase the battery, it would go up. If you were to increase the resistance, it would go down. So those two things are kind of battling with each other. Now in this case here, in case B, again, if we assume that these are identical light bulbs and they have resistance R, then you can look at this. And if I was to make this into the simplest circuit in the world, I'd have, again, I don't change the battery. I'm just sort of writing the battery again. But if I were to combine these two guys, all right, they're in series. For resistors in series, you add them up, so the resistance would be 2R. And so this is the simplest circuit in the world, and so the current in case B would be V divided by 2R. So what's happening here is by adding a second one in series, you're increasing the resistance and thereby making the current going through them less. And so the current going over here is V over 2R. And so one way to think about this is now the current going through this original light bulb, say this is the original one, is less than it was before, so it must be less bright. Another way that will be useful for us to think about this is using what's called Kirchhoff's rules. And I'm not sure if you've read or watched that video yet, but the idea is that when you go around a circuit, right, we always talk about potentials being kind of like mountain heights and stuff. And so as you go through the circuit, it's kind of like taking a hike in a mountain range. You might go up, you might go down, but when you come back to the same point, you should be at the same height you left at. And so the way we can think about that is here, this would be helpful too, is like suppose I start my climbing here. Okay, when I go through the battery lifts me up to some height, some potential V, maybe it's 12 volts, my favorite. And then as we go over here, as I go through these guys, I should be going down my voltage should be decreasing. There should be a voltage drop across the resistors, which should add up to being 0 at the bottom. So let's just say this is my favorite resistor, 12 volts. So as I walk here, I go up 12 volts. And over here, what should happen is I should go down 6 volts for the first guy and down 6 volts for the second guy. Lots of ways to think about this, but in this case, since they're identical, right, and they have the same current going through them, their voltage drop will be I times R. And so they have to be the same voltage drop. So you can kind of right away realize it should be a voltage drop of 6 and 6. Whereas this guy here, if I started here, I go up 12 volts from my favorite battery, and since there's only one resistor, I go down 12 volts. So this light bulb has the voltage drop of the entire battery where these two are shared. And so that's a little bit trickier in this case to think about voltage, but it's a good tool to have because there'll be some cases where it's a little bit faster to think about it that way. And so that's that case there. And so like here's an example, so you can go through and do this example if you want. And so now if we look at this in parallel, right, and again, what does parallel mean? Well, strictly it means that I can go from the top of the one to the top of the bottom, or I'm sorry, top of the first to the top of the second, and then the bottom of the first to the bottom of the second without hitting anything else except for just wires. And so these are totally in parallel. And so here we have a similar clicker question. So we have two circuits with identical batteries and three identical cylindrical conductors. Compare the current drawn from the batteries in the two circuits. And so again, let's just go ahead and say this is my favorite 12-volt battery, whatever, and say that this is R, and these are all, again, similar. And so here we're asking about compare the current drawn in the two circuits. And so what happens here is, in this case, again, this is the simplest circuit in the world. And so if I want to find the current of A, it's just sort of the same idea. Take the 12 volts divided by the R. That's the current that's leaving over here, 12 volts divided by R or whatever. Okay, so that's my current. Now over here, now if we were to make this into the simplest circuit in the world, replacing those two resistors with another one, so I'd still have the 12-volt battery, and you find that if you use the equation here, the resistance becomes R divided by 2. It's less resistance. By adding this extra one in parallel, you've reduced the resistance. Like one way to think about that is you've given the current like another path to take. Right, and so we can think about our resistance as being, a resistor, right? There's the sort of the area here, and then there's the length. And in our equation for resistance, it's rho L divided by A. So the longer it is, the more resistance, and the bigger the area, the less resistance. So by adding a second one, you're sort of increasing that area, giving it another path, and so the area would be increased and the R would be going down. So it's a little bit counterintuitive. But what it tells us is that the current in part B, right, is going to be 12 volts divided by R divided by 2, which gives me, 24 volts divided by R, so it's double. So the current that's leaving here is double. And so what happens is the current leaving here is double, right? And so it's 24 divided by R, right? And so right here it'd be like 24 divided by R. And then the current splits off here. So the person asked about this, but it splits off exactly so that 12 over R goes that way and 12 over R goes that way. Right? And so the question here is compare the current drawn from the batteries in the two circuits. Well, we can see that the current drawn is bigger in case B. So that is the answer to this particular clicker question. But the current going through each resistor, 1, 2, and 3, is the same. So when you add something in parallel, you add an extra path, and what that is essentially doing is that you can think about it as the current to the first one is unchanged, 12 divided by R, but you're kind of adding an extra 12 divided by R that comes around this way. Right? Now just be careful. This is, we're dealing with perfect resistors and perfect batteries, so it can be a little bit more complicated in real life, but this is how we're going to start out talking about this sort of thing. And so hopefully you can see that this parallel is the way that things are at our homes. Right? So the stuff at our homes is set up in parallel. So kind of like, if this was, your TV and this was your oven or something like that, when you turn on your oven, it doesn't reduce the power going to the TV, right? It's basically you have the current going to the TV, then you add another one going to the oven, and you can add more and more or whatever, right? If they were all in series, every one you added, the current going through all of them would decrease, and that would really not be good, right? Okay, so hopefully this helps. Put questions in for tomorrow's active time. Thank you.